Lastly, let's talk about flow control devices. They, of course, control the volume of flow in a portion of the hydraulic system. They are essentially different forms of restrictors in most cases. So for example, if you take a look right here, this is a flow control device. You see the symbol looks like it's being squeezed off or closed off. And that's essentially how a flow control device works. It reduces the size of the area at which the fluid flows through. This one's adjustable because you see that arrow at an incline. Now, one thing about restrictors is, of course, they do cause a restriction that potentially is going to cause back pressure. In this case here, when that restrictive flow, when it doesn't allow that flow, the pressure is going to back up, and eventually the fluid is going to go back through the pressure relief valve. So that's one. So how it generally functions. Keep in mind, though, it can potentially cause inefficiencies in the system because the system is going to a high level. This, for example, is going to a 5 gallon per minute. It's limited to 2 gallons per minute in this particular function, so 3 gallons are going right back to the reservoir. Keep in mind that's only a portion of the circuit. So for example, in terms of retraction, this bypasses the flow control valve. So this is one of these ones where it's going to have a slow extension and then a fast retraction. Another way of accomplishing this same thing, which will prevent a lot of this back pressure, is to use a bypass flow control valve. In this case here, we have the same basic setup where the fluid's going to come out. When this is going to be extended, 3 of the gallon per minute is going to go right down to the reservoir, and only 2 are going to be used to extend the load. When it's operated in the opposite direction, however, it's going to have that full fast retract because it's going to receive all 5 gallons per minute. So you can use flow control valves in a variety of different positions to accomplish tasks where primarily what you're going to be doing is controlling the speed of an actuator, how fast it extends and retracts, how fast a motor rotates, etc. This is All of these essentially use the same basic concept to control flow, and that is by controlling the size of an orifice, right? This is a simple diagram of it where we have a hole drilled through material, and the amount of fluid that's going to flow through here is going to be dependent upon the size of this. Keep in mind a couple of other things that's important in terms of this is the difference in pressure, right? A higher pressure difference between the inlet and the outlet is going to give us more flow. And the last thing that plays a role in this is the fluid viscosity. Thinner fluid is going to flow easier, thicker fluid is going to flow more difficultly. So higher fluid viscosity, you're going to get less flow. So these are all, this mechanism is, as I said, kind of basic, but pretty much all flow control valves rely on some version of this. So if you run into a situation where you need to calculate a flow rate, there's a variety of different types of formulas out there. And here's one example. So in this case here, we have QA, which is our flow rate. As we said, it depends upon the area. Keep in mind that's the cross-sectional area of our orifice. We have a coefficient of discharge, C sub D. This has to do with the viscosity of the fluid. Right? Different viscosities are going to have different coefficients of discharge. And then we have our pressure difference. Pressure difference is measured in pressure head and then modified to the proper units using gravity. So this is just one example. Different valve manufacturers have slightly different versions of this. And one thing to keep in mind that even though you may calculate a flow rate, you really need to check that and make adjustments on it. And in fact, over time, you have to check all flow control valves and make sure they're still operating over time. There can be wear, things like the different types of friction and things like that, and eventual changes in viscosity can all affect the flow rate. So this is something you need to monitor because it isn't something you can just set and leave. It will change potentially over time to a certain degree. The simplest type of flow control valve are, as I said, a restrictor type, and if they just basically reduce the size of the opening, they're non-compensated. Essentially, they just have a simple orifice. In some cases, you can actually just mount a plate with a hole in it, and they're going to essentially cause a certain pressure drop and going to reduce the flow. But keep in mind, as I mentioned, things like viscosity, pressure, etc. can change. And when those do change, these non-compensated ones, you're going to get a different flow. Here's an example of a basic type. Here's that needle valve. It's going to be opened or closed. You can set it. Once you set it, you're going to have fluid flowing through it. But keep in mind, if the fluid gets hot, you'll have more flow. If the pressure goes up, you're going to have more flow. So you can check the flow and adjust it, or you can build in some type of compensation. Keep in mind, this is designed to flow in this direction, and most of the times when you have a flow control valve, you'll have some sort of bypass with a check valve, so it allows free flow in the opposite direction. Most flow control valves are only designed to work well in one direction. Now, we can adjust for pressure by using that same sort of pilot pressure biasing spring combination that we saw earlier. We have the same needle valve that opens, right? And a fluid is going to flow through here. If the pressure goes up, that's going to compress this spring. It's going to push on this piston and compress this spring, and it's going to close off this portion of the valve, and this is what this whole compensating chamber accomplishes. If the pressure then drops, this valve opens more and allows more flow. So this prevents high pressures and pressure surges from causing greater flow through here. So this compensates for it. And what essentially does is it maintains the pressure difference. If the pressure was to go up, this closes off, causing a pressure drop, and it keeps the pressure the same, at least the pressure difference, I should say, on either side of this. If the pressure difference is the same, you're going to get the same flow rate. In addition, there are a couple of different devices that compensate for temperature. Essentially, we know what happens is as temperature goes up, viscosity goes down, and you're going to get more flow. So there's these devices known as sharp orifices. They're actually cut right into the material of these shapes in here. And it turns out that they are adjustable, but they don't adjust on their own. They essentially are fit here, and they're relatively immune to changes in viscosity. Not exactly sure the mechanism of this, and my understanding is these are pretty complicated to manufacture and maintain, but supposedly, just due to their shape alone, they're heat insensitive. Another solution is to take advantage of thermal expansion. As we know, when things get hot, they get bigger. As they get cold, they get smaller, and you can build in a heat-sensitive material. As it gets hot, it actually tends to close the valve. As it cools off, it tends to open the valve, so it compensates for the change in viscosity. So a couple different mechanisms can be used for this. Keep in mind, however, when we're dealing with hydraulic systems, we do want our temperature to remain relatively stable. So this would be only in situations where we weren't able to maintain a stable temperature. Another way to control flow and maintain a accurate flow rate is to, again, uses pressure. In this case, it has a bypass built in. So we have our main flow here. If the pressure goes up, it opens this bypass valve, and a portion of the fluid is sent back to the reservoir or bypassed to another port of the circuit. The nice thing about that is we don't have big pressure increases. We don't have the fluid being forced through small orifices, and as a result, you're not going to have as much heat generated. It's going to be more efficient in the overall function. So a little bit more complicated device, but has the long-term benefits of that reduced heat generated. The last of the devices we're going to look at are flow, essentially different types of flow divider valves. In this case, we have a single flow coming in, and we want to divide it equally into two flows going out. In this case, we have a spool, and we use our pressure to adjust it. If too much flow is going in this direction, it's going to increase the pressure, close this side off, and allow more flow in that direction. And essentially, in addition to this is a simplified diagram. We would have a spring to bias this, etc., just to keep it in its center position. The whole idea of this is when we're trying to get the same function out of both of these. You can also modify this. We'll see a few more modifications to it. Keep in mind, we can also use this for connecting two flows. We want the same amount of fluid to come out of both ones. So this can be operated in this direction to divide the flow. It can also be designed to proportionally combine flows. Now, if we want to have more flow going one area or the other, we can use a priority divider. This one actually has a spring built in, and in this case, the secondary outlet port is going to tend to be closed off. Most of the fluid is going to go to the primary one, unless we get enough flow. Enough flow is going to push on this and open the secondary port. Right, so this can be used in a device where we want most of the flow for the main function. If we have extra flow, it might go back to a filter or something like that. What it's going to essentially do is also act as a regulator when we're dealing with internal combustion engines. So if we ever have higher flow, it's only going to get a certain amount out, and then the secondary, any extra flow we're going to get is going to go out to the secondary outlet port, potentially back to the reservoir. The last of these actually combines two flow control valves to control the amount of distribution. So if you don't want 50-50, you can use a proportional control valve, and we can use two of these pressure compensated flow control valves, essentially working in parallel, and the fluid will go one the other. You can set these to be 50-50. You can set 75% to go one, 25% to go the other, etc., depending on what you want. Keep in mind they're only designed to operate in one direction. If we had fluid coming in the other direction, we see these built-in bypasses. Note also this long dashed dotted line. What this indicates is that all of these valves are contained in the same housing, and essentially they would look at like one device from the outside. Well, this wraps up our conversation on valves. As always, if you have questions, don't hesitate to ask them, particularly in the Q&A discussion forum where we share with other students. Other resources include the other videos and details on the website. Of course, you can always get in touch with me for additional assistance.